Hello everyone, welcome to the course on quantum theory of many-body systems in condensed matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to discuss the Anderson impurity model. And the Anderson impurity model is essentially a generalization of the resonant level model that we see in a previous class. Try to remember to put the link here. We're going to write the Green's functions for this model and see that unfortunately they do not close because of the interaction term, and we're going to discuss that. And then we propose a mean field solution where in this case the Green's functions do close, and we're probably going to do some illustration for a numerical solution of these mean field equations, and in a limit that is quite nice to work, and we're going to see some interesting results coming out of there too. All right, so let's jump right in. Okay, so let's start introducing the Anderson impurity model, and it is very similar to the resonant level model that we introduced in the previous class. I'll try to remember to put a link up here. So the Anderson model describes a localized level that we call the impurity, and usually you can think of this as say a magnetic atom, but we are only considered a single level of this magnetic atom, and this atom is coupled to a metallic band, so which is described by this other Hamiltonian here. So is a sum over states labeled by K. Here I'm considering the case where K is discrete, but it could be, I can view this as a continuum. And there is also the coupling term that you have this tunneling probability, or this coupling. This has dimensions of energy that mediates the hopping, or say the creation of an electron in the atom, in this what I refer to this creation operation. D of sigma creates an electron with spin sigma inside the level D, and destroys then an electron on the metallic band with label K and spin sigma. And of course you have the reverse process, so the whole thing is Hermitian, right? So you can destroy an electron here and create one there. So there is this tunneling between the metallic band, or this reservoir of electrons, and the magnetic impurity. So one important difference with regard to the resonant level model is that the Anderson model describes the spinful electrons, or fermions with the spin degree of freedom. So we're including here this label sigma, which counts or labels the SZ component of the spin of the electron, so it can be either up or down. So this level can be doubly occupied. So I can have two electrons here, but of course, due to the Pauli exclusion principle, the spins have to be opposite when you try to create two electrons here. One of them will have to have a spin up and the other will have a spin down. So let's look at this term, the impurity term. So the first term counts the number of electrons in the impurity and multiplies it by these epsilon 0, which is the energy associated with this level. So if you have one electron, you have 0 electrons, the energy associated with this term is 0. Then if you have one electron, it's going to be epsilon 0. If you have two electrons, it's going to be 2 epsilon 0. Now, the important difference with relationship to the resonant level model is that we now include this interaction term U, ND up, ND down. So what does this do? So it describes the Coulomb repulsion between the electrons, but only inside the impurity. So there's no Coulomb repulsion for the electrons here. It has to do with screening, and that's part of the model, and we're going to discuss that when we discuss the the interactions in the electron gas. But the point is that the model assumes that the electron-electron interactions are much more relevant here in this level, and not as much in the metal. Okay. So if I look at this term, what it means is that when I have two electrons in the dot, they will repel each other. It means that there is this extra energy, this, if you call it a charging energy, for instance, this extra energy, but that you must give to the system in order to put the second electron in there. So if ND up is 1 and ND down is 1, I get this extra term U. So it means that if I have one electron, I have energy epsilon 0. If I have two electrons, it's not going to be just 2 epsilon 0, but it's going to be 2 epsilon 0 plus this term here. And notice that this term is quadratic in the number, so it's quartic in the number of operators. So if I put these, I write this in second quantized form, it will have precisely that form that we saw for two-body operators, which is an interaction term. So it's quartic in the number of operators. So the other two terms are very similar to the ones in the resonant level model, have the band. So this is a free Hamiltonian, right? Diagonal and all. So it's just a number of electrons at a given level K with spin sigma. And there's this coupling term as well, right? As I mentioned, creates one electron in the dot, destroys one in the band, and so forth. So what you want to calculate here is precisely what we did in the resonant level model, which is the diagonal Green's functions for the impurity electrons, right? So we want to calculate the retarded Green's functions using the Zuborev formalism, and then calculate the imaginary part minus the imaginary part over pi, which is the spectral function of the level. So let's see how we can go about doing that. So to start to calculate the Green's functions, we need to write the equation of motion for these diagonal Green's functions for the impurity electrons. And that will involve these other retarded Green's functions connecting the electrons in the band and the electrons in the impurity. So to do that, we use the equation of motion in the Zuborev form. Notice here that involves the commutator of whatever operator appears in Green's functions with the Hamiltonian. So for this Green's functions is going to involve the commutator of this operator with the Hamiltonian, and for this one it's going to involve the commutator of CK sigma with the Hamiltonian. All right, so let's see how we calculate these commutators. And it's very similar to what we did for the resonant level model, except now that I have the spin degrees of freedom to care. But these two terms, this one and this one, we already derived when we calculated this commutator, but this one is different. Okay, so let's see how this one appears when we're calculating the commutator of CD sigma with H. Let me also mention that these other two are very similar to what it did in the case for the resonant level model. So let's focus on see how this one appears. Notice there's this sigma bar here. It means that it inverse of whatever this sigma is. If this sigma is up, the sigma bar is going to be down. So let's see how this appears in a commutator. Okay, so let's try to calculate this commutator with this term, which is the only one that we need, right? So let's take CD sigma with U and D up and D down. And for concreteness, let's take sigma to be up. So sigma bar is down. So this will be like CD up, U, and D up, and D down. And you can think of this term, since I can exchange, up and down here, right? These two commute. I can always think this term as something like that, CD sigma, U and the sigma, which is precisely that, and the sigma bar. So that's the same thing as here, but let's take sigma up just for concreteness. Okay, so this is going to be U times the commutator of CD up and the up and the down, which is going to be U, well, that's not right, just CD up and the up and the down minus and the up and the down, CD up. Now, ND down and CD up commute because, of course, ND down is going to be CD sigma down. Well, there's another helicopter passing here, but of course, since these guys are all CD down, CD up will anti-commute with this one and also anti-commute with this one, so I get a +1. So I get that these two commute. So I can just come here and commute these two here. And then I'll have the following. Oops, sorry. Let's go back to yellow. I have CD up, ND up, minus ND up, CD up, times ND down. Okay, so these commute. And this, of course, is the commutator of CD up with ND up, which we did calculate for the resonant level model, and we showed that this is just CD up. How do we get that? Well, you have to make sure that when you calculate this commutator, you do the trick of putting a dummy delta function here, so we get the order of the operators right. But that's what you should get, and that's what we get in the other terms as well. So the net result here is that this commutator equals U times CD up times ND down. Or in the generic case, where you have CD sigma U and the sigma and the sigma bar, this is just U CD sigma and the sigma bar. Okay, so that's the commutator that we need. So let's go back to the slide. Okay, now that we have the commutators, we calculated this. Let's substitute that and get the Green's functions. All right, so here's the Green's functions that we want. So you want the diagonal one, CD up, CD dagger equals the commutator between these two, which is 1, right? Plus this double time Green's functions of the commutator of CD sigma with H CD dagger. All right, so this is precisely GDD, right, equals 1 plus, now let's put the commutator here. There's going to be these epsilon naught, and then CD appears here. I'll get the Green's functions itself. Then there will be this term here. Yeah, I'm gonna leave that for last. Okay, there's be this sum here, TK. There's going to be appear a CK there, so it'll give me the GKD Green's functions. And that's essentially of course there's a sigma here, okay? I'm forgetting there, but this is KD. So far this is all that we did for the resonant level model. But now comes this, right? Now comes this. Double time Green's functions, where I'll have the ND sigma CD sigma, and the sigma bar CD sigma CD dagger. Now, what is this? This is definitely not one of those one of these Green's functions. So, but of course this will be a correlation function, right? So we'll call this D R of omega. I'll call this double time ND sigma bar CD sigma CD dagger. All right, so you'll say, okay, all right, what do I get out of this? Well, you can say, well, let's see what's the equation of motion for this guy. What's the equation of motion for that? Maybe if I write the equation of motion for this one, I'll get back to Green's functions such as this, where I have only one operator here, say a destruction operator here and a creation operator there, and then I can set my system of algebraic equations just as I did for the resonant level model, right? So you can say, okay, this, I'll call this A, I'll call this B, and I'll write the equation of motions for that. Would be something like that. So what's the equation of motion for this? Would be something like this. Omega plus times D equals what? Equals here, commutator of A and B, and D sigma bar CD sigma with CD sigma, which here I can see that this is not going to be a number. It's going to be an operator, right? So this is actually the anti-commutator. Well, this is fermionic because, yeah, this might be bosonic, but this is fermionic. So I'll have to do the plus sign there, okay? And this will give me the commutator of this, and the sigma bar CD sigma with H CD dagger. Okay, now things will become complicated because this commutator here will definitely not be proportional to a destruction operator like this. In fact, this will give me further orders, right? Why? Because when I calculate, say, imagine I calculate the commutator of this, and D sigma bar CD sigma with ND sigma ND sigma bar, right? This now, when I calculate the commutator of this guy with this guy, I'll have the other two number operators and the sigma bar there. So I'll still have at least like a two NDs there. So you say, okay, well, there might be hope, because maybe ND sigma bar square would be equal to 1, and you still be go back to a single operator. But it turns out this won't be the case, because I'll also have the commutator of ND sigma with ND sigma bar, and this will also complicate things. So feel free to calculate this, see where it takes you, and the answer is that this will give you a even higher order Green's functions that will appear there, and when you calculate the equation of motion for these higher order Green's functions, just as we did for dr, it will give even higher orders, and so on, so on. So this essentially does not close as we did in the resonant level model. So one way is that, okay, I'm just going to stop here and do some approximations like a mean field, or I keep doing that and I'll do the approximation in the next order. And notice this term here will be of order, there's a u here, okay? So there's a u, in this one is going to appear another term in u. So this scheme of trying to keep adding these orders, meaning say that I solve d, there's be this contribution, and multiply by this other u here, I'll have a term of order u square. So this is going to be of order u square. This is going to be of order u, right? It's multiplying d. But this one is going to be of order of u square. So if u is not small, then you're running into trouble. Okay. So let's see how we can try to overcome this when u is small. U is small, and we can try to do some mean field approximation for this guy. So let's go back to the slide. All right, so we came to the conclusion that this does not close. I can still write the Green's function, so there will be something like that, but it will have this higher order correlation function here that I'm calling d, that I cannot write in terms of d itself. Okay. So what do I do? Then I can do mean field. I can say that this within the mean field approximation, that if I evaluate the expected value of ND sigma, this and this uncouples from the rest, then this will be essentially given by this term. So the approximation here is that I can approximate this by the absolute value of ND sigma times CD sigma. And then this becomes just this expectation value, right? This average of ND sigma bar times the Green's functions of D. And then if I insert that back there, then the equation of motions does close. And here I'm putting this bar here to represent that this is a calculation in mean field, but this will give me a closed form. Notice that now this will depend on the expectation value of ND sigma bar, which I'll have to calculate using, say, the Green's functions for CD sigma bar, right? And I use that to calculate the Green's functions for CD sigma up, say, right? CD sigma. So in order to calculate the other, I'll need to calculate this, the ND sigma, and then use this to go into GD sigma bar and recalculate it. So you can see that there's a loop here. There's a self-consistent loop that needs to be addressed. So at t equals 0, the message here is that at t equals 0 or t not equal to 0, doesn't matter, but here I'm using t equals 0. This will depend on the Green's functions itself. So I need to make sure that this is accounted for. So the self-consistency loop will look something like this. I have an initial approximation for ND up and ND bar expected value. I use this to calculate, say, the mean field Green's functions for GD up using ND down as first approximation. Calculate then GD down using the first approximation for ND up. And so I have the two Green's functions calculated. And then I calculated the spectral functions for up and down, right? From the spectral functions, I can recalculate the expected values of ND sigma, and then I put them back here, recalculate the Green's functions, and hopefully that this will be something that will reach a convergence somehow. So let's make some very crude assumptions here. One of them is as we did just for didactic purposes, and actually is a good approximation for metals as well, is that the non-interacting part for the self-energy, and here I'm already introducing the term self-energy, which is everything that in the retarded functions comes after omega minus the level, the bare level occupation, and whatever here is the interacting self-energy, is the self-energy. This is the non-interacting part, and this has to do with the interaction U, okay? But let's say that the non-interacting term has this form, it's just a constant minus the imaginary part, which we call delta, and we saw that in the resonant level model. Then it turns out, and this you do in assignment, that you can have a closed form for the occupation, right? There's a bracket missing here. Okay, sorry about that. I'll try to correct. But essentially, it tells me that ND up is equals 1/2 minus 1 over P, the inverse tangent, or tangent, of ED naught corrected by this plus U ND down. So the opposite spin average expected value. So this tells me that this solution, there's a solution to these equations where ND up and ND down average value are not equal to each other. So this, if this happens, this is an kind of an artifact of the self-consistent loop and the mean field approximation that we're taking, where I'm allowing for the possibility of spin polarization. And that would be a spontaneous symmetry break-in, since in the system, the original Hamiltonian, there is no such symmetry. There's a symmetry between up and down. So in principle, the Green's functions would be equal. But here I'm allowing this symmetry breaking, so we will explore some sort of spin polarization or a net spin polarized magnetic moment in the impurity. And this we're going to discuss a little bit. Let's show some numerical calculations for this simple self-consistence equation, right? Where we can see that this indeed appears, especially if U is large. So it has this connection of the appearance of magnetic moments in the model when U is large. So yeah, let's take a look at it. All right, let's start by looking at the impurity Hamiltonian for the Anderson model, the one that has the impurity uncoupled from the other states, the metallic states. And let's call these the Anderson impurity states. So that's the so-called atomic limit of the Anderson model. So it all will depend on how many electrons I have in the impurity, right? I can have up to 2, and then I'll have 4 states, right, with different energies for depending on these configurations. So the first state is the one where I have nd equals 0. So I'm calling this precisely 0, right? So n up equals n down equals 0. So there's an empty impurity. It means that there is energy 0 for this state, right? Then the next state is whether the impurity is occupied by 1 up or 1 down electron. So the total number of electrons here is 1. So I can call this state E1. Is actually doubly degenerate, so some people prefer to label it by the spin, right? So you have 1 up and 1 down, so it's doubly degenerate. But that represents the state where ND 1 either up or down is 1. So, and of course the other one is 0, so this term is 0, and the energy is just epsilon 0, okay? And the final state is the one that is doubly occupied, meaning that I have 2 electrons, and this is not a good picture because it gives the impression that there's 2 levels, but there's only 1 level. What I'm meant to say here is that there's an energy difference between single occupation and double occupation that's more than just the single electron energy, right? Has this other term U here. So, but this one is also a state where nd equals to 2. So n up equals n down equals 1. So I have 2 here, have plus U there. So this is the atomic limit. Now what I'm going to do is try to couple this to the continuum of states, the metallic states, and see whether how is the occupation of the states will behave when I have the coupling now to the leads. So let's take a look at the blackboard. Okay, so let's draw this cartoon here, where I have here the band, or the band electrons that I called, which is just a system for non-interacting electrons, and I have many of them, and they're filled up to this maximum energy here, which I'm calling the Fermi energy, and I'm setting it as the reference point here. So all the energies I'm going to do are measured really relative to this Fermi energy, right? So this Fermi energy is 0 for all purposes here. Meaning that if the energy of the level is less than 0, meaning it means that there's is very favorable for the electron to go from here to here, because in doing so it will lower the energy of the system, okay? So in this case there is going to be a strong probability for this level to be occupied, okay? If epsilon 0 is larger than 0, let's start with the other case, okay? So let's start with this case. That means that the average occupation for the level is going to be approximate 0, right? So if the level is way above here, then it's energetically favorable for this electron just to stay put here, that doesn't go into the level, and everything goes. And everything works as if right, this impurity will remain empty. Now, if epsilon 0 is smaller than 0, then I can have this situation and D approximate 1. I have a single occupation here. As long as the energy required for the second electron, which is what? Is this plus this amount, epsilon 0 plus 1 plus U. Remember, the energy for the double occupied states is 2 epsilon 0 plus U. So I would add the energy for this plus the energy for that. As long as this plus U is larger than 0, then I'll make sure that it's more favorable to have only one electron here. Because, yeah, it's good to have an electron here. It lowers the energy, but if I want to have 2, then the energy is larger than 0. The overall energy is larger than 0, so again, nothing. So this, in this case, would be the whole ground state will have occupation approximately 1 in the dot. Okay? So here there's a sum over sigma, so that means that either n up or n down approximately 1. Which one of them? I don't know if the system is symmetric, okay, in principle. But in this regime, when epsilon 0 is lower than 0 and epsilon 0 plus U is larger than 0, I'm kind of guaranteed that the whole ground state will have 1 electron in impurity. Now, if epsilon 0 plus 1 plus U is less than 0, then here it becomes more favorable for me to have 2 electrons. Okay, so the sum over sigma approximately 2. So this is empty, impurity, singly occupied, and doubly occupied. Notice that I can do this plot of what would be the occupation, right? The total occupation as a function of E0. Okay? So I know what happens at 0. Well, this occupation would be small, okay? Something like this, very small. Now, around 0, and as long as this, and what is that condition here? This condition means epsilon d equals minus U. Then if epsilon d equals minus U, this becomes 0. So epsilon d equals minus U would be something like here, okay? Minus U. And then, so in between these two, so this is kind of 0. Let's put it 1 here, and I'll put 2 here, okay? So in between these two values here, I would expect this to be something around 1, okay? So that's again n up plus n down in these situations would be around 1, and below U I would try to see something like this, okay? This would be more close to U. So then here it becomes very favorable for the level to be doubly occupied, okay? And of course, the transition between these two is not discontinuous or very sharp. It's actually kind of smooth, right? It would be something like that if I would draw the total occupation as a function of epsilon 0. So remember, we're doing this mean field approximation. So at the very least, would like the mean field to recover this qualitative picture that we want. So let's take a look on a script that I did that calculates that the mean field occupation and try to reproduce this. Okay, so this is a script that I did, essentially solving those mean field equations self-consistently. So I have a loop here, set the parameters, and within this loop I update the occupation for up electrons and the occupation for down electrons according to that formula for the mean field that you're going to derive in the assignment, 1/2 minus 1 over p arctangent of E0 plus U times the down occupation divided by delta. And in the case of the down electrons, here comes the up occupation. So what I'm doing is I initialize the occupation at some number, and then I start calculating this, taking here the occupation obtained in the previous iteration and substituting here and essentially doing that self-consistency cycle. So I did this in Octave. You're more than welcome to write in your favorite scripting language, Mathematica, Python, Octave, whatever. And I'm going to try to do the plot of the total occupation here, right, as a function of epsilon 0, just like we did here. I'll do this as a function of epsilon 0 ranging from, say, minus 1.5 u up to u. So it's going to cover pretty much what's plotted here. So let's run and see what you get. Okay. So the first thing I want to share with you is this. The plot is qualitatively similar to what we had in our sketch. So look, this is looking good. For E naught very small, the occupation tends to 2. For E naught large, it will go to 0, and right in here in between -1 and 0 it stays around 1. Okay, so there's a couple tricks here. I'm not gonna go into detail how we're doing, but there's this small jumps here that you might want to take a look. Like, one thing that's important is that there's an even odd effect here. So you have to try to average between the previous not only the very last one, but an average between the one and the previous one in the self-consistency loop. And I'll show real quick that this can jump. I mean, sometimes you have something like that, right? You get alternation between small values and large values, and this will give you the average number will give you more or less the correct answer. But it's like a more technical detail. Now, one thing that is important here is how you initialize your first guess, right? Here I put the guesses for an up and down to be equal, and I put them to equal 0.5. So doesn't really matter. I mean, where you start, essentially this is quite robust. Even here, right, when for ED very small, they go to 2, so it doesn't really matter which numbers you put here, as long as they're equal. Now, if they're not equal, and I deliberately break the spin symmetry, let's say I put 0.6 and 0.4, could be the other way around, doesn't matter. Notice that what will happen. Oops, sorry. Let me go back here a little bit. Yeah. So the total occupation doesn't change much. That's the black line. But the up and down occupations, they start being equal, here. So in these regimes, even though I started them to be different, they really quickly converge to a situation where they're equal again. So like here, this point minus 1.5, I started with 0.6, 0.4, both converge to 0.9 something. Now, around the particle hole symmetry point, something weird happens. And then, even though the total occupation is around 1, it becomes spin polarized. And here is the spontaneous symmetry breaking in the mean field approximation. So if I would plot the difference between down and up, I would get this. So right here, I would have like 80% polarization appearing in this system. So this is spontaneous symmetry breaking due to the mean field approximation. So yes, it reproduces some of what would expect. This is, of course, is a feature of the mean field approximation. It spontaneously break the symmetry, but it points out to this idea that when you have a single impurity, a singly occupied impurity level, it might spin polarize spontaneously, at least in the mean field approximation. In general, we'll still obey the SU2 symmetry for the spin, but here it gives you the idea of that you might have a magnetic moment here, and in fact you will, even in the absence of the symmetry breaking. All right, so that was a taste on how the spontaneous symmetry breaking can happen in the mean field approach. We saw this numerical example for these coupled equations, and as I mentioned before, your assignment for this class is to derive these equations in this regime. But well, if we're not exactly in this regime, we can always do the self-consistency loop by calculating explicitly the spectral function here. Then it gives you a little bit more work. You might have to integrate this to calculate the expected values. So it's not as simple as the code that we did, but usually you still might have the solution, and you might still see some spontaneous symmetry breaking. So that's it for this class, and I'll see you in the next class where we're going to discuss the Schrieffer-Wolff transformation. See you there.